Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. We're doing Linear Algebra 1. This is Chapter 2, Matrices. Section 2.4 is Determinants and their Properties. Last time what we did was we gave the definition of an n by n matrix recursively. It's a horrible definition. You're not going to want to see it at all. This lecture, therefore, what we're going to do is we're going to define what a minor of a matrix is, what cofactors of matrices are, and computing determinants using cofactor expansion. We're going to give an alternate way of computing the determinant not using the definition, which is that horrible recursive sum. I'll write it out in the next scene and you'll see why. Then what we're going to do in the video after that is we're going to still further give determinant properties, because this can still take quite a long time computationally, so we're going to use cofactor expansion and determinant properties in unison to efficiently compute 4.5 billion by 4.5 billion size matrices, which is what the internet's using, etc. Let's start with minors and cofactors. The original definition from the last video was, for an n by n matrix, the definition of the determinant is this hot mess. Basically what that is the sum over all permutations in the permutation group as n. You don't need to know what those are, there isn't going to be a test, of the sinum of sigma, which is either +1 or -1 depending on whether it's an odd or even permutation. Don't worry about this. Times the product of the entries of A with their indices permuted by sigma. I didn't say that quite right. This is essentially brackets. This right here should be written as motivation for cofactor expansion. That's what this is. This is the definition. You saw it with the 2x2 and 3x3 explicitly it does work out that way. If you permute all the indices by the permutations of all the permutations in the group and then sum those up, you do get the number called determinant, which is a real number. Remember, every time this is a hot mess, but it's a single real number, and we're going to get many different ways of computing this using cofactor expansion. So try 2 of them, you better get the same answer. That's a way of checking. Before we give the definition of what a minor and a cofactor is for the ith jth entry of an n by n matrix, that even just sounds bad when I say it to myself out loud. I'm sure you agree. Before we give that horrible definitions of an alternate horrible definition of computing determinants instead of using the actual definition of this sum of this signed permutation business, what we're going to do is, just like last time, we look at a 3x3 determinant. It's defined recursively dependent on 2x2 and 1x1 determinants. What do we mean by that? First, we defined a 1x1 determinant is the determinant of a 1x1 matrix, which is just a real number, which is itself. So these are 1x1 determinants, and these are 2x2 determinants. And if you look cleverly, what we've done is what we're going to call cofactor expanded along the top row. And I know, it's exciting. Just hang on a second. She agrees. She likes cofactor expansion better than the definition. Wise cat. This is cofactor expansion along the top row. So I'm reverse engineering. Cauchy sees this and he says, oh, this is what we're going to call cofactor expansion. So first of all, he writes this a little bit. He sees we get positive, negative, positive. And in fact, we are going to get a checkerboard for the 3x3. It's going to go plus, minus, plus, minus, plus, minus, plus, minus, plus for the cofactor business. This always confuses students. This checkerboard enters right here, and that's how we deal with the checkerboard. This one is plus because it's -1 to the 1 plus 1, which is +1, so we get a plus. Here we get -1 to the 1 plus 2, which is a -1, so we get a negative and a plus. And so that we're getting these entries from the positives. But everybody always confuses the minors and the cofactors, and when they actually try to expand, they always get these negatives wrong, and this is how I always get you, is with negatives, I say. And so it's going to get you this time for sure as well. This thing right here with the -1 to the 1 plus 1, or I plus j, that times this sub 2x2 determinant, which, if you can see now, we're obtaining from this matrix by blocking off the first row every time, and then we got this 2x2 determinant by blocking off this row and this column. I know, just a second, we're going to do it all. And then this 2x2 determinant is obtained by blocking off this row and this column. And this cofactor, or this 2x2 determinant, which is where we're going to call a minor, is going to be obtained by blocking off row 1 and column 3, and that's where we're getting this one. These 2x2 determinants, which we're obtaining by blocking off rows and columns somehow, those are called minors. Once we put the -1 and the checkerboard together with the minor and multiply the associated, if you're M11, then you're going to multiply by -1 to the 1 plus 1. That creates a cofactor. So this sign thing is a cofactor. Cofactor with the -1, without the -1, without the -1, without the -1, they're minors, M11, M12, M13. And then this guy, everyone's always confused. Don't forget, you also, once you create the cofactors, you must multiply them by the associated entry of the matrix. Those guys come from the matrix. They're free. You're already given those. Everything else we have to construct. Now let's give the definition of minors and cofactors of every entry in a matrix, which is n by n, and then we will give the result of cofactor expansion to compute determinants. All right, now we can build the definition of what a minor and a cofactor is. Definition: let A be an n by n square matrix, and let Aij be the ijth entry of that matrix. Then for every entry of a matrix, so if you have a 3 by 3 matrix, that's how many? That's a square array, which is a square is a rectangle, but not all rectangles are square. Rectangle is never a square. Yeah, geometry. We're going to have an array which is m times n entries. In this case, it's a 3 by 3 matrix, so we have 3 times 3 entries, which is 9 entries, is my point. So what you don't see at first is, yes, unfortunately, and this is why you start disagreeing with, I thought I already had a row reduction method of finding inverses of matrices. Why are you building me this horrible thing with determinants and all this stuff? You've already forgot that now we're talking about determinants, that what did I want determinants for? Yeah, I'm going to build an algebraic formula for inverse matrices with determinants, and then determinants are so confusing that you forgot even already what we were talking about. So I want these determinant thingies and these minors and cofactors to compute determinants so I can get inverse matrices. And you're like, why? This is so complicated. Why are we doing this? Because otherwise you have to use the horrible definition, or when we use row reduction, you get horrible fractions, and this takes an extremely long time. Try to row reduce to reduced row echelon form a 5 by 5 matrix, even a 4.5 billion by 4.5 billion. I'm not doing that. So we want a better way of computing that. Now what we're going to do is, yes, we're going to have to compute for a 3 by 3 matrix, we're going to have to compute 9 minors and then 9 cofactors. For a 4 by 4, we're going to have to compute 16 minors and 16 cofactors. For a 5 by 5, okay, I'm pretty sure you see where I'm going with this. You're going to have to compute a lot of cofactors. I claim it's still better than doing row reduction of a 5 by 5 matrix. I would rather compute 25 cofactors than have to compute the 5 by 5 all the way to reduced row echelon form in most cases. That's why. So a minor for every entry in the matrix was that whole tangent. Minor for every entry associated to that entry is the n minus 1 by n minus 1 determinant. You get a one size smaller determinant of a matrix, which is one size smaller. And how do you obtain it? You just saw we deleted a row and we deleted a column, and that's how we got those 2 by 2 matrices. So we're going to get a slightly smaller determinant of a slightly smaller matrix by deleting a single row and a single column from that matrix A. Which ones? For the ijth minor, you delete row I and column J, so it matters. Mij definitely does not equal Mji. That would be deleting row J and column I. This would be deleting row I and column J. That is not going to work out the same most of the time. I'm sure you can cook one up where it does, but it's not going to be a rule. So order matters. Row I and column J. A minor is the thing that we actually compute. A cofactor is just extra. It is a signed minor. So it's not a new computation. Well, technically it is. All you're going to do is compute -1 to the sum of the indices. So if you have Cij, you take -1 to the I plus j, which is our checkerboard. Plus, minus, plus, minus, plus, minus, plus, minus, plus. If you do this -1 for all of the indices, you'll get exactly this sign. And then you multiply it by the minor. So if you take the absolute value, cofactors and minors are the exact same thing in absolute value. If you take them out, cofactors are simply side minors. You add the -1 checkerboard business to the subdeterminants you compute. I know. Let's compute one of these, and I'll show you all the cofactors, and then you'll see why I want them. Cofactors actually give us determinants. All right, let's do an example. Let's find all 9 cofactors Cij of the entries Aij for this 3 by 3 matrix. What are we going to do first? I'm going to do the first 3 on the top row, and then I'll do the 3 in the middle row, and then I'll do the 3 in the last row. So along the top row, because this is what Cauchy originally trains you to do, is cofactor expansion along the top row. This is what cross product and all of these other things are going to be. We put ijk in the top row. Let's see when we get there. Let's do the first row first. Therefore, I need C11, C12, and C13. This is how I like to do this. Now what I'm doing is running and practicing the definition. I have to read it or go back and pause the videos and write it down several times and remember what this definition is and try to absorb this. And then you do an example, and then you go back and look at the definition and do another example. Every time, eventually you can memorize what they are. So I regurgitate that first. then I'm not computing anything, so I don't have to worry about actually getting all the numbers right, because I have to do that as well. So I'm breaking it into stages. First, I'm remembering what the definition is, stage. These are signed minors. That means this one is -1 to the 1 plus 1 m11, which is -1 to the 1 plus 1 is -1 squared, which is 1. So this is just m11. It is a 2 by 2 determinant obtained by blah, 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 blah. I won't do that yet. Then this one, cofactor, is, I'm just doing the definition of cofactor minor business, not computing yet. This is -1 to the 1 plus 2 m12, which is, this is a negative number, which is going to be -m12, which is now negative a 2 by 2 determinant obtained from, well, just a second. And then the third cofactor I need is going to be -1 to the 1 plus 3 m13, which is, this is a positive number, or plus minus plus from our checkerboard. This is going to give me m13, which is a 2 by 2 determinant obtained by blocking off row 1 and column 3. Now I turn on my thinky brain even more, and now I have to actually compute. The way to do this also, it makes it nice. Let me use a slightly different color. For the first 3 along the top row, I'm going to block off the row 1 every time, because it's 1, 1, and 1, 2, and 1, 3. So every time we're going to block off a row 1 here. And then we're going to block off column 1, column 2, column 3 as we compute. So for the first one, we're blocking off row 1 every time. And for the first one, we're blocking off also column 1. This is the 2 by 2 determinant we're going to get. So I put that in there. This is going to give me 2, 1, 3, 4. If you want, do all of those first and then compute 2 by 2 determinants. But this is the Matryoshka doll. Once we start computing this, we get down to 2 by 2s, and this is how we compute 1 by 1s and then compute the number, which is called the determinant. So this one is now going to be 2 times 4 minus 3 times 1, which is 8 minus 3, which is 5. So that first cofactor, C11, is 5. Now, for the next one, -m12, to put that in here, we're going to block off row 1 and column 2 now, the T. What are we going to get? 3, 1, 2, 4. Therefore, this time we're going to get negative, because we had the negative on the outside, don't forget that. And then we're going to have 3 times 4 minus 2 times 1, which is -12 minus 2 is -10. And then in the last minor, we are going to block off row 1 and column 3, and this one is going to be our determinant. That's going to give me 3, 2, 2, 3, which is going to be 3 times 3 minus 2 times 2, which is 9 minus 4, which is 5. These are the first 3 minors, and these are therefore the first 3 cofactors. C11 was 5, C12 was -10, and C13 was 5. Let's compute the next 3. All right, this time what we're going to do is row 2. So for yourself at first, if you want to do this, draw 3 matrices where you block off row 1, and then draw another one, block off row 2, and then draw another one, block off row 3, and then it's really quick when you're on an exam, you're just referencing. But in my mind, I am always going to block off row 2 when I compute these 3 I know now, because I'm doing it along this row. Therefore, C21 is -1 to the 2 plus 1 m21, which is -m21, which is negative a 2 by 2 determinant. I prep myself. This one by definition is -1 to the 2 plus 2 m22. This is positive, which gives me m22, which is a 2 by 2 determinant, blah, blah, blah. This one is -1 to the 2 plus 3 m23, which is -m23, which is negative times blah, blah, blah. Now I switch gears, and now I've regurgitated the definition of cofactors over and over and over again, and hopefully by the time you watch some of these and try along, if you don't have a pen and paper, by the way, I should start mentioning this, and you're doing these along, you're doing it wrong, because this is not a passive sport, it's a participation sport, mathematics. So get a pen and paper and start computing these along, or writing as you watch them. Pause, compute. Now I switch gears. I'm going to block off row 2 every time, and then we're going to block off column 1 first. So that's the 2 by 2 determinant, 1, 0, 3, 4. 1, 0, 3, 4. If you want, now just keep going through. The next one is going to be 1, 0, 2, 4. And then the last one is going to be 1, 1, 2, 3. Then I can switch gears again if I want. Now just compute 2 by 2 determinants using the definition. This is going to be negative because I had that, and then this will be 4 minus 0, which is negative 4. When I have 0, I'm not going to compute. Yeah, I will, I guess. 1 times 4 minus 2 times 0, which is 4 also. And then this one is negative 1 times 3 minus 2 times 1, which is negative 1. Therefore, now I have the second row. C21 is negative 4, C22 is 4, and C23 is negative 1. Let's compute the last row's cofactors. Let's do the third row cofactors. So I'm going to block off that row for my mind, and then I can still see the entries. Therefore, what am I going to do with this? Again, regurgitate the definition. This is negative 1 to the 3 plus 1, M31, which is M31. This is negative 1 to the 3 plus 2, M32, which is negative M32, which is a 2 by 2 determinant. This is a negative 2 by 2 determinant. This is negative 1 to the 3 plus 3, M33, which is equal to M33, which is blah, blah, blah. Now I switch gears. I'm going to start blocking off rows and columns in my matrix to compute these subdeterminants, which are the minors, and these are the signed minors, therefore the cofactors. The first one is row 3, column 1, 1, 0, 2, 1. The next one is row 3 and column 2, 1, 0, 3, 1. And the last one is row 3, column 3, which is 1, 1, 3, 2. Now that I've done that, compute 2 by 2 determinants, AD minus BC, A11 minus A12 times A21. AD minus BC is much catchier. 1 times 1 minus 2 times 0, which is 1. This is negative 1 minus 0, which is negative 1. And this is 1 times 2 minus 3 times 1, which is negative 1. So C31 was 1, C32 was negative 1, and C33 was also negative 1. What do those do for us? Again, what have we done? We've learned how to cut down trees, but now I want to use those. Once we shear off all of the trees and get them into planks, we can compute determinants. Once we do that, we have planks, and we want to use the determinants to build the architectural house, which was the inverse matrix, which is an algebraic formula. We're almost there. Let's now use these in 3 different ways to show that what the next result is, and then we'll end the video. What do I want to use these for? If I use any 3 of these in combination and multiply them by this, I get the determinant. So just watch. Now that I have that information, what does it give me? Determinants. As many times as I want. More than you'll ever want to see. Alright, so quickly before I give the theorem about cofactor expansion to compute determinants, we are going to show with this example, now that I've computed them all, what they do for us. I've now got 1, 2, 3, 4, 5, 6 different ways of computing the determinant of this guy. Let's compute a few of those. Using these 3 elements, I have that the determinant of A we're going to write is A11 C11 plus A12 C12 plus A13 C13. And then everyone's like, where the heck did you get that? This is classic cofactor expansion along row 1. We already saw it. I showed you that these cofactors were negative 1 to the M11, which was all those 2 by 2 determinants. Now, we've computed those cofactors. They're just numbers. Where do I get this guy and this guy and this guy? From the matrix. This is A11, A12, A13. So this is immediately equal, I'll go slow. This is equal to 1 times C11 plus 1 times C12 plus 0 times I don't care. And why would I ever compute that actually once we know what we're doing? I shouldn't have computed that because I knew that cofactor entry was 0 and we're going to multiply it. So once you see now, when I have an entry which is 0, I'm going to multiply 0 times whatever the cofactor is. So I really don't care what that cofactor was. It will never affect, I don't even have to put it in there. It won't change the value. Now you can see that this is going to equal 1 times C11 was 5 plus 1 times negative 10, which is negative 5. And at this stage, it's like, well, I'm shooting the video and we probably checked and edited, but did I get the number right? I don't know. Sometimes I won't. If you catch it, put it in the comments. But you won't get me this time because I'm going to compute it a different way. Let's use these 3 numbers. Okay. The determinant of A is also equal A21 C21 plus A22 C22 plus A23 C23. And this is equal to 3 times negative 4 plus 2 times 4 plus 1 times -1, which gives me -13 plus 8, which is -5. I computed a different cofactor expansion along a different row, but I got the same number. Let's do it one more time. Let's use these three now along the first column. That's the one I'm actually going to train you to do. Get a leading one, kill below using determinant operations in the next video, and then we're going to cofactor expand along once I have a bunch of zeros, because then I don't care below. This is the combination of how we're efficiently going to compute, and then we're going to do Matrushka. Once we have a 5 by 5, I'm going to get a 1, and then I get 0, 0, 0, 0, and then I don't care, and then we'll have a 1, 4 by 4, and then I'll compute a 1, and then 0, 0, 0, I don't care, I'll get 1, 3 by 3 when I cofactor expand, and then I'll get 1, 0, 0, you know where I'm going with that, and then Matrushka, A, D, A, B, C, D, and then we compute, and we're going to have a way of computing determinants of all of these guys. It's a Matrushka doll of determinants, and I only want to compute one of them at a time, and that's how I'm going to do it, in combination of cofactor expansion and using determinant properties. These ones are coming in the next video. Computing along that column, which we're going to train you systematically in the next video to use. This is going to be the determinant of A is equal to A11 C11 plus this is A21 C21 plus this is A31 C31 along the first column now. That is equal to 1 times 5 plus 3 times -4 plus 2 times 1, which is 12, -12 plus 7, which is -5. You have 1, 2, 3, 4, 5, 6, and the original, if you really want, 1, 3, 2, 1, 2, 3. If you really want 7, you've got 7, Sesame Street, you can't use that. You have 7 different ways of computing determinants. Compute it at least 2 different ways, especially when you're on an exam, and you have a way of checking to see whether you did that correctly. Pause and meditate on what cofactors are. Now let's state the theorem, which put that all together. You can compute determinants using cofactor expansion along any row or any column of a matrix. You know who's that? Why you gotta look over that way? We're doing it this way. You know, this is Jasper. She's jealous of the 2 baby kitties that we got, so now she's coming down here to show her love. You know, you got to take timeouts with cats when they say timeout. Okay. All right, we're done this video. Not the course or math ever. It's never going to be done. Theorem: let A be an n by n matrix. Then I broke it into 3 statements. It's actually 2 statements. It's this one and this one. But this classically is how you first learn. And what you'll do when we compute cross product and all of these things most of the time. Stick to your guns. This is confusing, even though I just told you. I'm now going to contradict myself. Always use this one and then do one of these other ones to check whether you got this one right. So technically I'm not contradicting myself. But this is cofactor expansion, computing the determinant along row 1. But what the theorem magically says actually is you can, and I just show you so you are fairly convinced that it does actually work because I got the numbers right. That won't always happen because I'm bad with numbers. I like theoretical math. What we're going to do is we can do this along row I or column J, and I put it in color because this sum is confusing. Don't ignore this if you don't like that beast. But notice that I've colored it so that the I is not changing. The column I'm in is changing. And what that means is I'm cofactor expanding along the row so that the column will change. That's weird at first. But when you have the actual matrix there, now here, see J is staying fixed. I'm staying in the same column. And the row I'm in now is changing when I expand. So what that says is if you take all of those cofactors in any row or any column, multiply them by their associated coefficients or entries in A, and then add that up, you always get the determinant of that n by n matrix. Please subscribe right here, hit the notification bell below. Next time what we're going to do is give you a bunch of properties. I'll focus mostly on 3, but I've got about 8 or 9 or 10, or I'll stop at some point, but we'll use 3 main ones to efficiently get a leading one in a top left corner and then get a bunch of zeros below and then do the Matrushka trick. I get patent pending. The Matrushka cofactor expansion done by wizards. See you next time.